Hello, this is Jack Jackson back again. We're going to be looking today to continue our series of these little lectures on summarizing what we found out about doing transformations. And this one is going to be talking about vertical and horizontal strains and dilations. So, basically, expansions and compressions. Okay? So, remember that when we talked about this earlier, we were talking about transforming relations and symmetry a little bit. And first we talked about translations, which we got by adding or subtracting something from x in the table. And of course that was replacing x by x plus or minus something for horizontal, and for a vertical replacing y by y plus or minus something. So now instead of doing addition or subtraction, let's do multiplication or division here. So what we're going to do is replace in the formula x by x divided by some constant, say a, where it's a positive constant a. And when we do this, what's going to happen in the table? Well, let's think about it. Let's look at the example here. We got y equals x squared in blue, like we've looked at several times. And then if we replace x by 2x, then we get this formula in red here. Now notice what's going to happen is, remember we said the formula is backwards, so what we're going to really do is leave the y's alone. So the y coordinates are the same when we line up these image and pre-image points here. So all these y's in the original, okay, here, are the same as the y's in the new one. So the original is called the pre-image. New relation is called the image. And what we're going to really do is not multiply the x by 2, but do the opposite, which is divide the x's by 2. So negative 4 here becomes negative 2. Negative 3 becomes negative 3 halves, or negative 1.5. And so forth. So that's what we're doing. So what does that do to a coordinate? Well, to the graph. Well, it takes a coordinate and leaves it the same height, the same y value, but the x value is half of what it was before. So what are going to be fixed? Well, fixed points are going to be the points when you do an x of 0. So because half of 0 is still 0. So in this case it's the origin, but in general it's going to be anything that's on the y-axis is going to be fixed. Points that are say 1 away from the y-axis, like the point 1, 1, or the point negative 1, 1, those are now going to be the same height, still 1 for the height, but the distance from the y-axis, the x value, is going to be half as much. So now it was 1 away, now it's a half away. If you look down here, this one was 2 away from the y-axis, now it's only 1 away, it's half as much. This one down here was 4 away, now its image is only 2 away. So what's happening is the points are coming in closer to the y-axis. So they're not really all moving the same direction. Well, they are in the sense that they're moving toward the y-axis, but that makes some of them go left and some go right. So it's however far away it was from the y-axis, it's only half that far now. So the points that are out to the right are going to go still to the right, but not only half as far. And the points that are left are going to be still to the left of the y-axis, but only half as far out. So the points end up moving toward the y-axis. How far? Well, halfway. So the points that are further away end up moving in more than the points that are close. And of course, points on the y-axis don't move at all. Okay, so there we go. It's half as wide. So we squished it, compressed it. That's called a horizontal strain by a factor of 1/2. Now, if this was the top of the function and it didn't have the arrows going on forever, then notice that the range here is from 0 to, well, somewhere between 11 and 12, and it's going to be the same range for the new one, but the domain is half as big. So if this went from, oh, I don't know, negative, well, not quite to negative 4. Let's say it actually went all the way out to negative 4. Then the new one would only go out to negative 2. on the left, and on the right it went out to, so say the original actually went out to 4, then the new one's only going to go out to 2 instead. Okay, here we have another example. Y equals x cubed, and we replace x by x over 3, x divided by 3. Then what we really do is multiply the x's by 3 and of course leave the y's alone. So again, I just make up a table here, pick some x's that we're interested in, use the formula y equals x cubed to find the rest of the y's, and then I line up my table in such a way that the y's are the same, the y values, because y is not changed. It's only x that's changed. How do we change the x? Well, opposite of the way it looks in the formula, it looks like we're dividing x by 3. In reality, we multiply x by 3. So, for example, negative 4 times 3 is negative 12. Negative 3 times 3 is negative 9. Negative 2 times 3 is negative 6, and so forth. Well, what's that going to do? Again, things are going to be at the same height, so they're going to not move up or down, but they're going to go farther away from the y-axis, 3 times as wide. So this time we've stretched it out or expanded it horizontally. We haven't changed the height of it at all, but we've made it wider, 3 times as wide. Let's look at an example here. How about if we start with the circle? Let's see, x squared plus y squared equals 1. That's a circle, sometimes called the unit circle. It's centered at the origin, radius 1. Now what's going to happen if I replace x by x, say, divided by 7? What's going to change and what's going to stay the same? Well, the y's should stay the same. So right now the y's go from negative 1 to 1, or the range is from negative 1 to 1. That's not going to change. But the domain right now goes from negative 1 to 1 as well, and now it's going to be 7 times as big. So it's going to actually go all the way out to negative 7 and all the way out to positive 7, and so it gets stretched. And so the image is a shape we call an ellipse. Sometimes you'll hear the word oval. Okay, so it's an ellipse. It's been stretched out. So an ellipse is just a stretched out circle where it has a strain where it's strained in this case in the horizontal direction but not the vertical. So it's stretched more in one direction than the other. Notice that this does not map a congruent figure to a pre-image to a congruent image. It's distorted some. It distorts both distances and angles. So notice the distance between pre-image to image here in the original from the left and rightmost points is 2. Well, now the distance is 7 times that. It's 14 this way. But distances vertically weren't changed. The distance from here to here, the top to bottom, was 2, and it's still 2. So, distances are distorted, angles are distorted. If we did an angle from, let's say, from the top to the origin out to here, it's a right angle. Well, that one's still a right angle, but if we do from here down up to, say, in the middle here, well, you get a 45-degree angle. It's no longer a 45-degree angle if we find its image point across here. So it distorts angles, it distorts distances. But still, in some ways, kind of basically the same shape. Okay, so now what's going to happen if I take that one and replace y by, say, y divided by 4? Well, that's going to stretch the maroon one there, 4 in the y direction. So now the red one has been stretched there. So if we start with the blue one, we can stretch it, well, the way we did is 7 and the x by a factor of 7 times as wide, and then we made it 4 times as tall. And so notice that ends up changing the domain. Instead of negative 1 to 1, now it goes from negative 7 to 7. And the range was negative 1 to 1, and now it's negative 4 to 4. So you can see how those stretches affect things. Okay. Also, we have this situation here. So let's go back to, let's get an h of 0. There it is. And a k of 0. So we'll put this back on top of where it started. So now preimage and image are the same. By the way, a transformation that leaves every single point fixed is called the identity transformation. It's kind of a boring transformation, but it is a transformation nevertheless, where every point is just mapped to itself. Okay? Now, if we change the A value, let's change it to 2. Now everything is twice as far from the y. I ended up doubling the x value, so it's twice as far from the y-axis. So notice where we started with the square root of x function. I've looked at this before, and again, well, I can change this function if I don't want it to be square root of x. What if I just want it to be x squared? There we go. It affects it. It's still, the red one is still twice as much. Or if I want to change it to x cubed, still twice as far out, stretched. Or what if I want to graph, just 2x? Again, however far out we are, we're twice as far now. So the original one, for example, has this point 2,4. Now we're at the point 4,4 for the image. Okay, I'm going to go back to my original one. X to the power 1/2. Okay, and notice again we can look down here and see our pre-image and image points. Again, with this applet, you can change these numbers to anything you want. It's going to show up. Let me just show you. If I change this to 2, that's 2 comma square root of 2. Square root of 2 is approximately 1.41. And then you see the image point there, the same y and the twice as big of an x. I happen to pick some values that are perfect squares, so I get nice integer values here. Whole numbers, in fact. Okay, but we can see that as a is changed, something different happens when a is negative. We'll talk about that actually in our next video. But right now we're going to stay with positive a's, and the bigger a is, the further this gets stretched out. Okay, if a is 1, then that's the identity transformation. It's not really a strain at all, just doesn't do anything. But when a is less than 1, notice it gets compressed. So if a is 1/2, for example, now we go halfway in. So it's closer to the y-axis. The point 0, 0 is its own image, so you see pre-image and image down here. They're the same. Okay? But this point 1, 1 is still 1 for the y, but it's only 1/2 for the x. It goes halfway in. This one moves further. It was at 9. Now it's going to be at 4.5 for the x. But the y stays 3. This one here, the new one's at 8, so the original one was out here at 16. If I could change my window, or I could change my window, if I go out there a little further on the window, it's going to be at, well, here it is. It's 16.4, and then the image is 8.4. And this C16 is 25, is 12.5. It's the image of the point, with the pre-image point 25.5. So again, the smaller a is getting closer to 0. Whoops, let's get this back. Let's reset. I want b to be 1. Okay, and we want, right now we just want a positive, but as it gets smaller, things are compressed in closer to the y-axis, and as it gets larger, they get stretched out further away from the y-axis. If you really follow this C13, for example, you can just see how it's being moved. Okay, let's see, going back, so you can kind of see what's going on there. Okay, well, it's pretty obvious, I think, what's going to come next. If we can replace x by x over a for a constant a, positive constant a, and that gives us a stretch horizontally. Then if we replace y by y divided by b for some positive constant b, that's going to give us a vertical stretch. In the case of changing x to x over a, we got to stretch away from or toward the y-axis, and the vertical strain here now is going to be, when we replace y by y divided by b, that's going to be a moving toward or away from the x-axis. It's away from the x-axis, a stretch or expansion when the b is bigger than 1. When b is less than 1, still positive though, between 0 and 1, it's going to go toward the x-axis. And of course if b equals 1, then it's not really a strain at all. It's just everything stays left alone. Boring. Okay? So here we have y equals x squared again. We look at y over 2 equals x squared, or 2 times x squared. And that is, we replace y by y divided by 2. So again, we're going to leave x alone this time, but we're going to multiply the y values by 2. Remember again, it's backwards of the formula. If you think of the formula as replace blank by blank. Replace y by y divided by 2. We're going to actually multiply the y's by 2, which you see that we've done there in the table. Again, I've lined it up, and this time since it's the x's are not changing, my pre-image and image are lined up so that the x's are the same. And now we see pre-image and image there together, pre-image in blue, image in red, and you see things are moved away from the y-axis, the x-axis. So things are moved straight up or straight down. In this case, everything's above the axis or on it, so the one that's on it doesn't get moved. That's the origin. That's our fixed point. Okay, you can see it right here in the table. You can also see it right here on the graph. Anything on the x-axis is going to be fixed. But anything that's off of the x-axis is going to move further on the same side of where it is. So the blue points are above the x-axis, so the red points will be above the x-axis as well, just twice as far above. Okay. Similarly, over here in the next example, we have y equals x cubed in purple, and again you see the table for that. Again, I could have picked anything I wanted. I just picked some interesting points there. And if we replace y by 3y, we get the green graph, which could also be written as y equals x cubed and then over 3. And of course what this does is leaves the x's alone, but then it takes the y's and it's going to divide them by 3. We got some repeating decimals this time for some of them ones. And so everything's this third as far from the x-axis. So the whole graph is sort of 1/3 as tall. 1/3 as tall definitely makes sense if you have a finite domain and range like we did with the ellipse that we looked at just a minute ago. But in the case of an infinite one, 1/3 of infinity is still infinity. So this is still infinitely tall in one sense, but in another sense you can still think of it as being 1/3 as tall. It's definitely 1/3 as far from the x-axis for each point in the image compared to the corresponding points in the pre-image. So in general, a strain requires that we specify a line. We'll call the line the axis for the strain, and a positive strain factor C. And then we move points perpendicularly toward or away from that line so that distances, the image points from the line, are C times their corresponding distances of the pre-image point. From the line, and the points are on the same side of the line. They don't flop on the other side of the line. We're using a positive constant here. You're actually going to move toward the line, compression toward the line, when your C is between 0 and 1, and a C bigger than 1 will be a stretch, expansion. We're only going to talk about the ones that are easy to do, the strains about the x and y axes. So just replacing x by x divided by constant and y by y divided by constant. So this turns out to be a non-similar image. As we looked at before, we saw, for example, in the ellipse that things got stretched out, and so we don't have a congruent image anymore. If we cut it out, we couldn't really place one right on top of the other. So it distorts distances, and it also distorts angles. But still kind of the same kind of shape. So still very closely related to the original one, just been stretched or compressed a little bit. The fixed points are going to be the points on the axis of the strain. So if you're going to replace x by x divided by constant, points on the y-axis are fixed. If you're going to replace y by y divided by constant, points on the x-axis are fixed. Remember, the x-axis are points when y is 0, the y-axis are points when x is 0. So symmetry, if it's going to have symmetry with respect to this transformation, you're going to have to be able to stretch it and still get the same thing. It's kind of hard to come up with those, but one example is if you've got a horizontal stretch, if you've actually got a horizontal line, when you stretch it, there's always enough points on that line to take the place of the ones that you stretched out, and since it's infinitely long, both directions, goes on forever, then you're still going to get an infinitely long horizontal line. And similarly, a vertical line has symmetry with respect to vertical strain. I'm not going to say these are the only possible ones, but these are the only ones we're going to talk about. We're not going to worry about this too much. Now, I want to talk about a dilation. A dilation is also called a size transformation. And what we're going to do with the dilation is we're going to apply the same amount of vertical and horizontal stretch. So look at this. When we took this circle that we started with here, and when we stretched it more in one direction than the other, it's no longer a circle. What would it take to make it still be a circle? Well, we got to stretch it the same amount in both directions. So if I replace this by, say, x divided by 8, then I need to also replace y by y divided by 8. And now it's going to be stretched out 8 times as wide and 8 times as tall, which ultimately is 8 times as big all the way around. So the way you want to think about this is every point, image and pre-image point, is 8 times as far away. So let me just graph a line that goes through the origin. And so if you take an image point, which is right here, however far this is out on that line, you go out on the same line 8 times as far, and this point right here where they intersect is the image point. So the pre-image is right here on the original circle. Let's get rid of these ellipses. Okay, so the pre-image, these are a little too close to the same color, but you got the lighter blue for the pre-image and the darker blue for the image. And the origin is the center of our transformation. And so what you have is you've got of our dilation. So it turns out you've got them in this order. You've got the pre-image, or the origin, the pre-image, and then the image when your factor is bigger than 1. And these will be in a straight line. So it's a distance from 1 out here. It's going to be a distance of 8 out to this next one. Or if you're going this direction down here also. Or if I take any line through the origin. Here's another line through the origin. Where this line crosses this circle on the first circle is a pre-image point, and its corresponding image is this point out here. So everything's 8 times as far away from the origin. Now if I compress this down and say replace x by, say, 2x, and then do the same for y, replace y by 2y, now everything's half as big. And again, you get these points, pre-image, image, and origin are in a line. This time, though, it shrunk, and we have pre-image, or we have origin, then image, then pre-image. So the image is between the origin and the pre-image, whereas on the one out here that we started with, the dark blue one, where the factor was bigger than 1, it's the pre-image that's between the origin and the image. Going back to our GeoGebra sketch, I have a sketch here where we can stretch. We've looked at this already, where we can stretch. If we stretch these the same amount, let's say A is say 3, and then also let B be 3, now it's 3 times as far away. So if you actually connected these up with a straight line, notice that we have 0, 0 to 1, 1. This 3, 3 is on that same line. They're in a straight line. And let's see, let me make both of these a little bit smaller. Let's make it 2. Okay, so this is twice as big. So we should see pre-image or origin, pre-image, and image in a straight line. So now we got 1, 1, and then 2, 2 here. And I can't show it because it's not on the screen. Well, I can do it. I can just got to change my points a little bit. Let's do this here. So let's pick something instead of that far out. Let's pick something closer. Let's just pick 2, and let's see if you can see this on the graph. So here's the point 2, and then square root of 2, and its image, that's the original one right here, B14, and C14 is out here. So notice that goes to the right 1, right 2, and then up about 1.4. So if it's on the same slope, if you go out right 2 more and up another 1.4, you're at here. And so that means that the original origin, the pre-image point, and its image right up here are all in a straight line. Okay. Okay. So here it is in a table. If we replace in the red one, y equals x squared, we replace x by x over 2 and y by y over 2. We're going to actually double all the lengths. Everything's going to be twice as far away from the origin, straight out from the origin from where it was. And we're going to actually double all the x coordinates and double all the y coordinates. Similarly, over here we got y equals x cubed as the blue one, and then the purple one is 3y equals parentheses 3x cubed. So we're going to replace y by 3y and x by 3x. That's the same amount of stretch vertically and horizontally again, so that's a stretch away from the origin by a factor of 3. So everything's 3 times as far from the y from the origin, and it's 3 times as big. And I tried to show how pre-image and image points line up by drawing line segments from the origin out to the image or pre-image, whichever one was further away, and so you can kind of see how they line up. So in general, a dilation, or sometimes called the size transformation, requires that we specify a point for the center of the dilation and then a positive dilation factor, let's say C. And then what we end up doing is move points along the line containing the pre-image point and the center of the dilation, so that the distance from the image point to the center is C times the distance from the pre-image point to the center. So actually what you do is you start by making a half line, a ray, starting at the origin, or the center of your dilation, which ours will always be the origin, and make it out to the original point, and then have it keep going as a ray. Then measure the distance along that ray to start with, multiply that distance by whatever our factor C is, and that's going to tell you how far out to go along that ray from the origin to get your new image point. So again, we're only considering dilations about the origin. It turns out that this time we don't get a congruent image, but there's not as much distortion going on as we had with just a horizontal strain or a vertical strain. Actually what happens is we get a similar image. Okay, so the image of the dilation is not necessarily, it's not congruent to the original pre-image, but it is similar to the pre-image. What does that mean? Well, it means that angles are preserved. So if we were to take say a right angle, and then actually I can make a right angle fairly easy with an absolute value equation. So let's do this. Let's do y equals, actually I can actually write it like that. Y equals absolute value of x. That's a right angle. Now if I take this and let's shift it, place x by x minus 5, now we're 5 away. So 5 to the right. So let me get rid of the original one, and then we have that one. So we have that right angle. Now, if I were to do if I just replace, say, x by x divided by 2, okay, notice the fixed point was the one on the y-axis. That's the one that didn't move. But notice we have a wider angle. The angle is distorted. But if I go back and now replace y by y divided by 2 as well, now we get a new one, and it is, in fact, the same angle. See, it's still a right angle. You can kind of tell by looking at it there. So notice that when you stretch it more in one direction than the other, angles are distorted, but angles are not distorted whenever you stretch it the same amount. So you can do a size transformation there. Okay? So essentially this is what happens when you go to a photocopier and you say enlarge or shrink it in a photocopy. It's doing a dilation. Okay? But it turns out that the lengths are proportional. So so if we go back up here, for example, and let's say the distance between, okay, say 0, 0, and 1, 1, that's a distance of the square root of 2 if you use the Pythagorean theorem. Okay? Well, when you multiply everything by 2, 0, 0, and 2, 2, that distance is twice as big, so that's going to be 2 times the square root of 2. But it doesn't have to be between the center. That wouldn't involve the center. What if I take something that doesn't involve the center, like from 2, 4 to 3, 9? Okay, we could use the Pythagorean theorem on that. Let's see, that's a delta x of 1, a delta y of 5, 1 square plus 5 square, that's 26. That's square root of 26 there. Let me check it out. Let me show you the details of that so you can kind of follow along there. So we're taking the point 2, 4 and 3, 9 in the original. And the distance between them is the square root of 9 minus 4 square plus 3 minus 2 square. So it's a delta x, actually I did delta x second, but that's okay, of 1. So let's see, we have a delta y of 5. So that's 25 plus 1 is 26, and the square root of that's the distance. But now we take the corresponding points over here, and those two are original. The corresponding ones are here, 4, 8, and 6, 18. 4, 8, and 6, 18. You're going to see the distance is not the same, but let's see what happens. Let me do it this way. Well, I did a delta y first, so I'll go ahead and do delta y first here again. Negative 18 or minus 8 is 10 for delta y. Delta x is 6 minus 4 is 2. Usually I write that the other order. But so distance 1 is here. Here's distance 2. That's 100 minus, that's plus, always in the middle, plus 4, square root of 104. Okay, 104 I can factor so 26 is 2 times 13. So that won't reduce. So that's 26 is reduced. 104, however, we can reduce. It's 4 times 26. . 4 is 2 squares, so this is 2 square root of 26. Look what happened. What's our dilation factor? It's 2. We're multiplying the distances from the origin by 2, okay, or we're multiplying the vertical and horizontal distances, and so the distance between any 2 points is going to get multiplied by 2. So the originals were, those original 2 points here were square root of 26 apart. Their images over here, there's the image of that one, there's the image of that one. The distance between those two is twice as big, 2 times that original square root of 26. So, and this happens no matter where we are, so it turns out that the distances are proportional, and the proportionality number there is the same as our scale factor, or our dilation factor. So, everything's twice as much there in terms of distances, but angles are the same. Okay, so that's exactly what we mean by a similar image. So if you were in elementary school, you might say this is the same shape but a different size for the pre-image and the image. Fixed points. The only fixed point is the center of the dilation. So in this case, the origin. So since we're only doing origin-centered dilations, that's the only fixed point we're going to have. And in both of these cases, that was one point that was actually on the graph, so you can see it in the table here in both cases where that origin stayed the same. Well, not many things are going to have symmetry with respect to dilation, but one example would be a line that goes through the origin. Because if you take a line through the origin and you stretch it out away from the origin, all those points will stay there. Not really going to look at any other examples of that. So we'll come back in our next video and pick up talking a little bit about reflections. In this one, what do? We talked about vertical and horizontal strains, stretches in the x and y direction, and then dilations, which has a stretch in the x, stretch or compression, in both the x and y direction, but the same amount. So we get a similar figure.